Let's talk about the so widely heard term as the Anthropocene. Perhaps majority of people assume that the Amazonia is least disturbed place on Earth, but is it so or not? In Amazonia, human activities that occurred hundreds of years ago in the pre-European era left long-lasting effects on the forest, and this we call ecological legacies. Ecological legacy, which basically refers to the influence of an event on an ecosystem and its persistence over a given time period, and is a term that has been widely used in succession studies. If to talk about the ecological legacy, then it is worth to mention Europe as well, where over the last 100 years, significant land cover changes occurred. Forest coverage has increased substantially due to different reasons, and therefore, if one goes into, let's say, the Latvian forest and claim that it is a natural forest, ecological legacy must be considered. And as you might remember from previous lectures, nearly all forests in our region were cut at some point in the past, therefore disturbed. For millennia, natural processes such as tectonic uplift, volcanic climate, erosion, and sediment transport have shaped the Earth's surface. However, in the recent history, a different global force has been raised, and this is obviously humanity. Anthropogenic landscape now cover an extent of Earth's land surface as many other globally important ecosystems. In these landscapes, human activities create characteristic geomorphic features, for example, channels of irrigation, terraced systems on hill slopes, surface mining. And these features can significantly affect Earth's surface processes, example, erosion, runoff, sediment transport, and deposition. And humans have the potential to amplify geomorphic processes. Geomorphic processes as such, they are the physical and chemical interactions between the Earth's surface and the natural forces acting upon it to produce landforms. It is maybe odd, but we can consider humans as bioturbant agents. Charles Darwin was the first to describe the effects of animals on the structure of the substratum in which they live today. With this term defines as the reworking of soils and sediments by animals or plants, and bioturbation by humans, if we can call anthroturbation, is a phenomenon without precedent in the Earth's history. Humans have become the dominant element in many Earth's surface processes at different scales, to the point that human activities can be considered distinct from but comparable to the effects of climatic or tectonic transformations. Humans move increasingly large amounts of rock and sediment during various construction activities and therefore are a geological agent. Erosion rates from mining and agriculture that are among the highest rates in the general can exceed the rates of most natural erosion processes. Mining activities and cultivated fields from different regions most likely erode at rates typical of mountainous terrains, for instance. Agricultural terraces are among the most evident and extensive signature of humans on different landscapes of the world. Since ancient times, one can find agricultural terraces in different topographic conditions and used for various crops. Agricultural terracing introduced several critical issues: increase of slope failures and hydraulic erosion processes, and redistribution of chemicals. Human impact in floodplain modify the spatial distribution and the rates of hydraulic and geomorphic processes, and this might result in land degradation and geomorphic changes. Changes in geomorphology respond to several complex and interdependent factors. For instance, mines, quarries, urban areas, and all types of infrastructure represent an estimated 13% of such changes. Compared to other anthropogenic topographies, mining occupies a relatively smaller amount of land worldwide, but it leaves clear signatures on the surface. The main characteristic of such an important topographic signature is its persistence in time, so they can persist over the long time periods. With the extending of mining to large scales due to the mineral demands, mining-related hazards and disasters in the Earth's surface will become more and more severe, inducing risk also for the landscapes surrounding the mines. Scientific community is now debating the fact that we are living in the new geological epoch, stratigraphically distinct from the Holocene, and that's why we call this the Anthropocene. In common usage, the Anthropocene refers to a time interval marked by rapid but profound and far-reaching change to the Earth's geology, currently driven by various forms of human impact. But where did this term Anthropocene came from? To get to the term Anthropocene, we first need to return 200 years in the past. It was Sir Charles Lyell who, for the first time, used the term the Holocene, which means recent whole. Therefore, he put certain foundation of how we name the time in which we are living now. Growing geological, geomorphological, and geographic evidence indicated that during the Holocene, mankind's activities gradually grew into a significant force as recognized early on by a number of scientists. For instance, George Perkins Marsh on 30 September 1847 gave a lecture to the Agricultural Society in Vermont, USA, where talked about the human impact. His ideas later were published in a book with the title Man and Nature, and more than 160 years on, it really does pay to reread his work as it seems remarkably actual today. It also shows that he was decades ahead of most of other thinkers on this subject. After all, he delivered his lecture a decade before John Tyndall began to explore the thesis that slight changes in the atmosphere's composition could cause climatic variations, and it was a full half a century before Svante Arrhenius proposed that carbon dioxide emitted by the enormous combustion of coal by our industrial establishments might warm the world. Marsh was not an environmental scientist, but he believed that all consumption must be reasoned and considered with the impact on future generations always kept in mind. Antonio Stoppani, a founder of Italian geology and also paleontology, I would say also a geoarchaeology, rated mankind's activities as a new force which in power and universality may be compared to the greater forces of Earth. Stoppani already spoke of the Anthropocenic era and thus the term Anthropocene as such. Vernadsky, the founder of geochemistry and biochemistry, in 1926 recognized the increasing power of mankind as part of the biosphere. And he wrote, "The direction in which the processes of evolution must proceed, namely towards increasing thought and forms, have greater and greater influence on their surroundings." So he were underlying the force of human. In 2000, Paul Crutzen and Eugen Stoermer proposed that human modification of the global environment had become significant enough to warrant termination of the current Holocene geological epoch and formal recognition of a new Anthropocene epoch. Unfortunately, Paul Crutzen died in 2021, and therefore both these authors are gone, but their legacy is still ongoing, especially when we're talking about the Anthropocene. Although their term Anthropocene was not new, they cite A number of similar proposals for terminological recognition of human dominance of the Earth's ecosystems that had been made over the last 140 years or so. Crutzen and Stoermer proposed that there are certain points according to which the beginning of the Anthropocene can be set. These include human population, chemistry, cattle, and mining. So let's unfold each of these points more closely and begin with human population. Crutzen points correctly that the expansion of mankind, both in number and per capita, exploitation of Earth's resources has been astounding. To give a few examples, during the past 3 centuries, human population increased tenfold, 10 times more than it was before, and these numbers are still increasing, as you are aware. This population increase is accompanied by growth in cattle breeding. It has been estimated that we utilize about 1 to 2 cows per average size family each year. Not to mention meat consumption is a rocket high at the moment. Crutzen and Stoermer underlined that over the last 2 centuries, the global effects of human activities have become clearly noticeable. Secondly, data retrieved from glacial ice cores show the beginning of growth in the atmospheric concentrations of several greenhouse gases, in particular carbon dioxide and methane, and these changes coincided with James Watt's invention of the steam engine precisely in 1784. As 4 point, they mention biotic assemblages in most lakes began to show large changes. So that means changes in lakes and aquatic ecosystems in general. Indeed, several climatically important greenhouse gases have substantially increased in the atmosphere, such as carbon dioxide by more than 30% and methane by even more than 100%. More nitrogen is now fixed synthetically and applied as fertilizers in agriculture than fixed naturally in all terrestrial ecosystems. So that shows the shift from the natural to human-related neutral fertilization. Furthermore, the release of CO2 globally, about 160 teragrams per year, to the atmosphere by coal and oil burning is at least two times larger than the sum of all natural emissions occurring mainly as marine sulfides from the oceans. Not to mention volcanic eruptions, as we will see here and there. There are significant changes, but they cannot be set starting at mid-18th century, as these authors claim. To assign a more specific date to the onset of the Anthropocene is somewhat arbitrary, but many scientists and their research groups try to pinpoint this boundary. Importantly, we still do not have a certain point for this boundary. Alternative temporal boundaries for the Holocene and Anthropocene boundary do exist, but each of them have both pros and cons, meaning they all have some link to human activities, but only few of them actually could be real candidates. In 2009, the Anthropocene Working Group of the Subcommission of Quaternary Stratigraphy was established to consider the evidence for environmental signatures that could be uniquely attributed to a new epoch, and this working group is responsible for producing a recommendation to be considered by the International Commission on Stratigraphy, including a requirement for defining its lower boundary. You see, there is a certain way how new epoch, as well as we call it in geology, can be defined. It is not enough if one scientist publishes an article on this topic and says that he thinks that the Anthropocene started in mid-18th century or other time period. There are certain protocols to fulfill at first, and to meet a consensus within the worldwide scientific community after which such new epoch actually can be established. The recognition of human-induced stratigraphic marker that may underpin certain stratotype or point or so-called golden spike, which with which to define the lower boundary of the new epoch is essential to this process and hence the definition of the Anthropocene itself. A global boundary stratotype section and point, or abbreviation GSSP, is an internationally agreed upon reference point on a stratigraphic section which defines the lower boundary of a stage on the geologic timescale, and a majority of these points and sections are based on geochemical and paleontological changes. And the detailed succession of stratigraphic signals, though the boundary interval is a basis for interpreting the correlation of that boundary into successions at other localities. And importantly, the stratotype must be older than one human generation. So that means there should be this fingerprint of changes traceable after several decades and lifespans of the humans. The whole process can be visualized in a rather simple scheme where it all begins with a JSSP proposal, then work within the working groups and subcommissions. If at least 60% or more vote yes, proposal goes further until it is ratified, meaning changes are officially approved and used worldwide. In order to establish new anthropogenic epoch, it is necessary to define a stratotype, a layer which is characteristic for the Anthropocene and is found worldwide. Unfortunately, lack of such precise layer forms a stage for various discussions. Okay, so as you know, then the Anthropocene must be defined based on certain physical or chemical sediment characteristics. Based on what chemical element or object remains we could establish the Anthropocene? Well, that's the good question. And let's look on some of these. For instance, the rise of plastics since the mid-20th century, both as material element of modern life and as growing environmental pollutant, has been widely described. Discarded in various ways after use, we see plastic widely around us as litter, unfortunately. And plastics might be used as markers of the age and character of the sedimentary deposits that they are buried. Much in the way that geologists use, let's say, fossils to characterize the certain sediments. Therefore, plastics are relatively easily recognizable when they are large pieces without, then we can recognize them without any sophisticated analytical equipment. But the plastic has this tendency to break apart in smaller and smaller pieces, and then we need really costly and sophisticated equipment to recognize these particles in the sediment. There has been dramatic rise of produced plastics from the less than 2 million tons manufactured in 1950s to the 300 million tons made annually today. So these are enormous amounts of plastic what we are producing worldwide. Plus, the plastics are proving to be much more mobile than other human-made materials, such as, for instance, glass or ceramics. And plastic fragments with densities more than 1 gram per cubic centimeter, including PVC, sink in seawater. They can then be moved in shallow water and by various gravity-driven currents in deep water before finally being deposited. It is hard to grasp, but the plastic can be found deep into the waters in Arctic and Mariana Trench, which, as you know, nearly 12 kilometers deep depression in the ocean. So therefore we can say, yeah, we did it. We polluted with the plastic everywhere. So that's kind of sad thing to think that our impact is so heavy on the nature. Plastic in Arctic, plastic in deep oceans, in the snow, in Siberia, also in the air. Plastic is transported by the air as well. And the geological longevity or the lifespan of the plastic polymers is poorly known, mainly because these are novel materials that have been in the environment for only decades, and plastics are nearly um, probably long-lived elements on human timescales if we consider human life as a marker, especially when the plastic is buried in the earth and the sunlight is not directly reaching the plastic. Then the plastic can survive, let's say, being kept and encapsulated into the sediment. While if it's open air storage, then the plastic comes brittle and then fragmented into smaller pieces, as I mentioned. However, there are also other scientific discoveries that there are indications that certain microbes degrade plastic, but this scientific research is still in its early stages, so it's too early to say that nature itself will consume the plastic. So we still need to carry out carefully what we are doing with the plastic. It's worrying because anthropogenic debris, including plastic found in wildlife, raise some concerns. Vast amount of seafood rich in plastic debris is on a sale for human consumption, and there are scientific um, publications also on that we can find microplastic also in placenta of newly born child mothers, and therefore the plastic can transform into the human body as well. Um, well, if we talk about the debris, then in Indonesia, anthropogenic debris has been found in 28% of individual fish and in 55% of all seafood species. So 55% of all seafood species we find micro um, debris from human activities. Similarly, in the USA, anthropogenic debris has been found in 25% of individual fish and 67 of other seafood species. So 25 in fish species and 67% in other seafood species. All of these anthropogenic debris recovered from fish in Indonesia is plastic, whereas in the USA, this is mainly debris of fibers. Therefore, variation in debris types likely reflect different sources and waste management strategies between different countries and continents, I would say. Regarding the ocean floor, sedimentation rates are low, and the Anthropocene will be represented by millimeters in stratigraphic thickness. So this means that when plastic accumulates, after a longer time period, new sediment will cover this plastic and so forth, while the pressure will be high enough to compact this layer into only tiny millimeter. So, and most of the seafloor is bioturbated or mixed by benthic organisms. Therefore, the plastics over depth of a few centimeters will, like the rest of the sediment, it will be mixed with older deposits and separated from them by a diffuse gradational boundary. So they will not be as a distinct marker, but most likely a mixture with other sediment. And this is one of the practical issues of applying a plastic marker over a very short time period for the geological new epoch recognition. Recognizing the exponential growth of plastics production since the 1950s, the onset of this marker of the Anthropocene is likely to be diffuse and not perfectly isochronous and in a stratigraphic succession. So it will probably not be the best option what to choose. For instance, a significant presence of plastics in the marine and terrestrial environments was not recorded until the late 1960s to early 1970s. Therefore, despite their utility for plastical stratigraphy, namely recognition and characterization of the Anthropocene deposits, plastics cannot be expected to act as a primary marker for precisely defining the start of the Anthropocene. And that means that their concentration, distribution, localities are not synchronous or homogeneous all over the world, because we have some hotspots where we can find plastic more and somewhere less. So that can be challenged to use this marker as well. Air pollution. So aviation emissions are increasingly significant contributor to anthropogenic climate change, and global aviation emits about 1.04 billion tons of carbon dioxide every year, and this represents about 2.5% of total CO2 emissions per year. When to consider the full flight, which includes emissions from takeoff, cruise, and landing, aircraft emissions impact air quality and emit small particles, which are basically nanoparticles. These particles, alongside chemical metals, settle out on land and also in oceans, of course. There have been studies which indicate that these possibly could be used as the anthropogenic markers, but it is not clear whether they truly would last long enough for calling as a decent marker, and not to mention that their recognition within the sediment might be an issue, because their distribution, as you see, highest concentrations are in certain path and certain continents, not in all locations. Uh, well, air pollution is crucial, and we see that in a few generations, mankind is exhausting the fossil fuels that were generated over several hundred million years. And the main oil and natural gas regions overlap, and as you probably know, then during the oil extraction process, vast amount of natural gas coming out as a side product is burned. And these numbers, of course, are just staggering. Well, during the high temperature fossil fuel combustion, fly ash particles are produced and emitted to the atmosphere along with flue gases. These are two main particle types: inorganic ash spheres, which are derived from non-combustible minerals present within the fuel, and spheroidal carbonaceous particles, or SCP, which result from the incomplete combustion of the pulverized coal particles or oil droplets themselves, and are a component of the black carbon. So we are talking here about the black carbon pollution, which is basically air pollution, but they tend to also settle down somewhere. And these particles, again, to stress, they form during the high temperatures, not like diffusing from the cars or airplane. And so we are talking about heating power plants. Well, they have no natural sources due to this high temperature, and their characteristic shape, color, and morphology make them as excellent indicators of contamination from this industrial source. Further, they preserve in a range of accumulating media, including freshwater and marine sediments, peat, and ice. So we can find them everywhere. The SCP data from 71 lakes across the world have been compiled in 2015 publication by Rose, and this study covers Europe, North and South Americas, Asia, and one site south to Australia. The point is that across all these sites, SCP record begins in the mid 19th century, with the rapid increase starting from 1950s. And this dramatic increase in SCP deposition is concomitant with many other indicators of great acceleration, as we call it, including, of course, primary energy uses, and is linked with the post-World War II increase in the demand for electricity and the introduction of cheap fuel oil. The duration of this rapid increase varies between the regions because the SCP concentration peaks are often followed by a decline in inputs. But the rise in SCP is about around 1950, and this is recognizable in all over the world. Um, yeah, there are several reasons for decline in some regions after the peak is reached. Uh, and for instance, some kind of filter systems are new technologies are used, applied. Also, the source of fuel has changed, and the regional decline of heavy industry as well. Therefore, while some features of SCP profiles vary regionally, the rapid increase in the 1950s appears to be a global signal, which can be attributed to the human activities. SCP are reliable stratigraphic marker for a new geological epoch because of long-term preservation. However, carbon-rich particles with a bubble-like textures, well, that means similar to these, thought to have been formed by bolide impact into organic-rich geology around 65 million years ago, before present and have been observed at the Cretaceous-Paleogene boundary. These are thought to have been produced by low temperatures, like 300 to 800 degrees temperatures, and they are still preserved, but as I said, they are not exactly look-alike as SCP, but a similar type of particles. Therefore, the source of these particles might be promising in the terms that we can predict that the SCP will have similar sediment and preservation values over the time, and if SCP preserve similarly well, and there is no reason to suggest that they will not, then they would easily meet the criteria for a long-term stratigraphic marker. Yeah, so these might be used as for defining the Anthropocene boundary. Next, one huge discussion field is about radionuclides. Finney and Edwards proposed as the beginning of the Anthropocene precise date, 16th July 1945, and their arguments was it marks the first atomic bomb explosion that initiated a period of atmospheric testing, the results of which are seen in radionuclides in ice cores and lake cores. At least one human generation has passed, which is important for establishing a stratotype. The radionuclides in cores can be taken as the stratigraphic signal that most closely coincides with what has been termed the great acceleration of human impact on the Earth's systems. So again, great acceleration, so this term is widely used when we consider human impact. Standard stratigraphic practice requires a significant, globally widespread and abrupt signature, and the fallout from nuclear weapons testing appears most suitable for this. The appearance of plutonium-239 makes a good marker. This isotope is rare in nature, a significant component of fallout, a stable marker in layers of sedimentary rock and soil. On a global scale, the first appearance of plutonium-239 in sedimentary sequences corresponds to the early 1950s. can be used to define the Anthropocene in sites located between 30 and 60 degrees north of the equator, because there it was maximal fallout for these testing episodes, and probably only within undisturbed marine or lake environments these radionuclides can be detected. But again, uh, if we consider the worldwide evenly distributed signal, then you see there are some mismatches between the both hemispheres. And the long half-life of plutonium-239, which is 24,000 years, makes it the most persistent artificial radionuclide detectable by modern mass spectrographic techniques for about 100,000 years. Whether it's enough, well, that's a question. 100 years in geological terms is clearly nothing, but well, there are discussions that we can use this one at least to support Anthropocene boundary. Plutonium-240, also a product of nuclear weapon testing, is less abundant and has a shorter half-life, hence not so good for a marker. Therefore, plutonium isotopes are considered by some authors as valid for setting the Anthropocene boundary. But the question, of course, when we consider this half-life of the elements or of these elements and radionuclides, then there is some shortage. The short half-lives of cesium and strontium limit their potential to serve as geologically permanent markers, which are, again, different kind of radionuclides. Then americium-241 has a deeper water distribution than plutonium, being more readily transported to the bottom of deep oceans on signing organic particles, and so may be a more suitable signature in the undisturbed deep water environments. However, the lower abundance of americium and its only 432-year half-life would make it useful only for 1,000 or 2,000 years. C14 shows a bump peak at 1963, 1964, and this has been proposed as a potential marker as well, and can be detectable only 50,000 years though. So radionuclides are promising, but their half-lives and longevity and detection from the sediments is the major concern. How can we detect and why we should use them if they are not traceable after, let's say, 100,000 years, which from the geological point of view is then questionable. Before considering fallout radionuclides serving as a marker horizon, past and future circumstances should be evaluated as well. For instance, one example, the advent of long-range aircraft capable of deploying nuclear bombs drew military attention to the Arctic, which was the shortest route between the US and USSR during the Cold War. In April 1951, the US and Denmark signed the Defense of Greenland Agreement of building 3 air bases in northwestern Greenland. In 1959, after several years of intensive ice sheet research, the US Army Corps of Engineers built a Camp Sentry, which was excavated at 8-meter depth in the ice sheet's porous near surface firn. So specific firn, it's not like a ice sheet yet, but it's in the middle. So therefore, it's porous near surface firn, not ice what we considered true ice. It's going there, but not yet. And well, these engineers they studied the feasibility of deploying ballistic missiles within the ice sheet, so for the military purposes. This subsurface provided year-round accommodation for between 85 to up to 200 soldiers, and was powered by a portable nuclear generator and logistically supported by pulling supplies across an over snow trail. And this project called Iceworm and was uh, it terminated in 1963 because it was rejected, too costly, too not efficient enough, and year-round operations at Camp Century ceased or ended in 1964. Seasonal operations continued until 1967, but it was not year-round operations anymore. And after that, when the base was abandoned with a minimal decommissioning, so there were left many these kind of structures and elements there because engineering design of the era assumed that the base would be preserved for eternity by the next snowfall. So they assume the snow will cover this base and everything will be captured in a capsule. So everything will stay put there and nothing will change. The last reported visit to the abandoned Camp Century site was in 1969. Aside from the reaction chamber of the portable nuclear generator, which was removed for destructing testing of later, all infrastructure remained in the collapsing tunnel network after the 1969 survey. So the picture from 1964 and a few years later, obviously there are tremendous changes. Everything is collapsing. So the Camp Century tunnel network covers approximately 55 hectares, and based on modeled vertical advection rates, the majority of solid waste is now likely buried at approximately 36 meters depth. Due to the relatively efficient movement of liquids within permeable fern, the burial depth of refrozen sumps is less certain, but it is unlikely they are now shallower than 65-meter depth. A notable exception is diesel fuel, which was stored in rigged tanks at tunnel depth and may even remain liquid to date, although the tanks have likely ruptured. So that means, indeed, this kind of setting has now is covered by the ice, but it is not in that shape what it was when they left the site. And the fuel in these conditions are specifically made to not freeze, and therefore it's liquid still. But what has been assumed that these tanks where this fuel was kept, it's probably they have been broken, and the fuel most likely has been now within the ice contact. And independent airborne ice penetrating radar observations today record strong anomalous reflections at locations and depth consistent with inferred tunnel positions and modeled waste depth. So we are using geophysics to study more what's going on within the ice. The studies imply that the inferred vertical advection rate profile suggests that solid and liquid waste will reside at depth of 67 and 93 meters in 2090. So this means that we might see that this kind of object will get even deeper over the time. Since the 1960s, however, the scientific community has recognized the Greenland ice sheet to be more sensitive to climate forcing than previously thought. If to compare between 1900 and 1983 and recent climate change, Greenland ice sheet has accelerated mass loss. So Greenland is having less and less ice, and that might be some kind of issue also for this certain kind of example with these wastes of different origin. Given an anticipated to kind of solid waste depth in, let's say, in 100 years from now, at 6744 meters, we can say that it might be the melting region, which then could expose wastes at the ice sheet surface. However, meltwater can interact with a deep firn more rapidly via vertical percolation. So, observations indicate that surface meltwater can percolate downward 10 meters through firn in a single summer melt season. So, therefore, it's a concern that it either will be open after the ice will melt from the top, or the meltwater flow downwards can increase the speed of movement of ice sheet itself, and or uh, kind of uh, runoff of these chemical elements might easily go into the North Atlantic Ocean. And abundant US military base in the melting Greenland ice sheet may expose oceans to toxic pollutants by the end of the century. As I mentioned, yeah, so ballistic missiles and other chemicals, radionuclides and toxic pollutions is there. And this is only one example about which we now know. There might be also other examples. And many tons of toxic waste remain buried under the ice and continue to be an environmental concern, particularly with the general trend of ice mass decreasing and the possibility that these materials will eventually get exposed to the surface, and therefore isotope concentrations thus will be different in northern hemisphere. Therefore, these signals of human activities are not fixed in one event, but might be catastrophes such as Fukushima, for instance, in Japan, where we have natural hazards all over the region. Therefore, the signal of radionuclides is probably not the best idea to use for the Anthropocene, defining the Anthropocene. The next one is the lake and the landscape change, of course. Anthropogenic effects are also well illustrated by the history of biotic communities that leave remains in lake sediments. The effects documented include modification of the geochemical cycle in large freshwater systems and occur in systems remote from primary sources. Surrounding catchment is tightly linked in this case. And I have been giving also some examples about the lake responses to different kind of these kind of influences. How, for instance, algae community changes over the time or under different kind of pressure scenarios. Trophic state of the water body is changing due to natural and anthropogenic factors. For instance, Lake Arashi, which is located in central Latvia, central northern Latvia, then we can see that it still is polluted today, in the sense that humans started to live there during the Iron Age, and since that, this human pressure related impact on the lake ecosystem has been never released. So the lake still continues to attract human impact through various ways. And this is an issue worldwide, and different point of sources from cattle breeding and manuring of agricultural activities around the lakes can be traceable. And if to look closer to the territory of Latvia, then our analysis indicates significant shifts in algal composition in our lakes since 1200 AD. Therefore, we argue that the reference conditions for these lakes can be assigned with the age before this time. Therefore, all other changes affecting lake ecosystems are on top of that, and it is not clear why then 1950 would be the beginning of the Anthropocene, because we see that the lakes and water bodies and landscape has been modified significantly already before this time, 1950, and these changes are recognizable from the sediments. Furthermore, if to look on global scale, then Latvia fits well within human impact on lakes and their surroundings, indicating significant human impact already 3 to even 9,000 years ago. So it's not an exception, and we see that the human impact with changes on the landscape, in the landscape, and the pollution can start at different time frames all over the world, and as you can imagine, then there is no one consensus about the Anthropocene, the beginning of the Anthropocene. Therefore, to conclude today, I would say that there are several potential proxies based on which the Anthropocene can be established, but it will take long before we might consider this as a new epoch. Therefore, the term Anthropocene can be used to indicate human impact, but without a specific start of the date. And the Anthropocene is not officially ratified, and therefore we are still living in the Holocene. So we can use a term Anthropocene to indicate human impact, but it's not the new official epoch, or as we would like to claim. Thank you. See you next time.